Greetings everyone. Today we are presenting our work on Smoother, a smooth, renewable, power-aware middleware, to be presented by Lianho Zhu, Hitar Chopra, and Chunli Peng. The full presentation and a short elevator pitch are available on YouTube, linked here. A bit of the background and reasoning behind the paper. Computing systems are more energy hungry than ever, and as they grow, so do the bills and carbon emissions. Renewable energy offers a clean and cost effective solution, but comes with challenges like fluctuation and intermittency, making it unreliable and hard to use effectively and efficiently in real time systems. Most current solutions try to balance energy stability and utilization, but they fall short, leading to poor performance or high costs. This provides the perfect opportunity to introduce Smoother, which is a middleware that makes renewable power more usable and reliable. Let's look at a bit of a context. Modern systems rely on a microgrid that combines the main grid, design generators, and renewable sources. While brown energy sources like grid and diesel are stable, they're expensive and polluting. Renewables are cheaper and cleaner, but non dispatchable. To model power usage in such systems, we use a linear power model as shown here, where the output of the server, which is a function of the CPU usage, is the idle power plus the difference of the full power minus the ideal power times the CPU utilization. Since this paper focuses on wind energy, we look at how wind energy is calculated. Wind energy is defined using a piecewise function shown here, which on the surface looks quite complex, but in simple terms is no power is produced if wind is too slow or too fast, which is the first and the fourth case. Moderate wind speeds generate variable power, which is the second case here, and between rated and cutout speed, turbines produce consistent output. This behavior is unpredictable minute to minute but follows recognizable patterns, and these patterns are exactly what Smoother leverages to optimize energy handling. A few challenges mentioned were high fluctuation. It is naturally expected that wind power frequently spikes or drops. This instability affects the grid and internal clusters. It increases the rock-off or the rate of the change of frequency and forces frequent load migrations. It requires large, costly battery systems to smooth the energy supply. The graph here shows wind speed data over a 24-hour period, and notice how the wind speed is highly variable with constant peaks and dips, almost similar to a price graph. The second challenge is operational instability. Systems struggle with how often they must switch between energy resources. This leads to constant virtual machine migrations, energy source switching, poor use of backup batteries, among other things, all of which hurt the system performance. The third challenge is the supply demand mismatch. Renewable power generation and workload demands are almost never perfectly aligned. Trace analysis from real data centers shows that green energy often goes unused because it's produced when systems don't need it. The diagram illustrates the growing demand supply gap, where the EE initiatives are the energy efficiency programs that slow down demand growth, and the new energy sources are the renewables which boost supply. The fourth issue is ineffective scheduling. Existing schedulers only delay jobs while renewable supply is high or costs are low, but they don't account for how unstable the energy might be. What is the solution? Well, solution is that Smoother provides two complementary techniques to solve these challenges. The first is flexible smoothing, commonly referred to as FS in the paper, which works in moderately fluctuating regions. It predicts and reduces volatility by optimizing battery usage essentially clearing and discharging to smooth out power spikes. The graph shows the raw output of energy, which is the wind energy over time, and you can see how it fluctuates rapidly. Using flexible smoothing, we use a battery storage to absorb excess power during peaks and reserve it during dips, resulting in the smoothened power curve. The second is active delay, commonly referred to as AD. This identifies deferrable jobs like batch tasks and shifts their education to times when renewable energy is more available. This diagram represents how we apply active delay to deferrable workloads. Each sloped line shows the progress of a job over time. The horizontal arrows indicate how each job is shifted. For example, D equal to 12 means a job is shifted by 12 time units, and by doing this smart shifting, we can match job execution times with periods of high renewable energy supply without missing any job deadlines. Let us now summarize what Smoother brings to the table. It's a cost effective and synergized design where both FS and AD work together to improve stability and energy use. It's a practical mitigation scheme which works with finite capacity batteries, not just ideal ones. It's generalizable, and while the paper focuses only on mainly on wind energy, the design can be applied to any renewable resource, including solar. And lastly, it's tested and reproducible because the authors use real workloads and renewable energy traces in MATLAB and even release the code for public use. Now we move on to the nitty gritty of the algorithm and design.
Hi, I'm Niehao Zhou. I will introduce the paper method. First, the objective is to quantify wind power fluctuation. We can use a specific formula, and this will allow us to partition wind power curves into distinct regions. For example, region 1 shows stable output, while region 2, especially its second part, is much more unstable. And the goal is to maintain a steady wind power output, which reduces the need to frequently switch to other energy resources. If the wind power is unstable, how can we get a steady output? Yes, we can use batteries. When wind energy is abundant, the battery charges, and when it's insufficiency, the battery discharges to support the system. We divide the process into small intervals, and U represents the renewable power generated at each interval, and S represents the corresponding battery discharging amounts. A represents the final power output of the system, and we transform this into an optimization problem, minimize the variance of A, and consider a simple case where the wind follows a sine function plus a constant, and the batteries offset this with a negative sine function, resulting in a constant output. However, real-world challenges make this much more complex. Battery capacity's limitations mean that during periods of high winds, we may not store all the excess energy, and the limited discharge rates might not fully meet demand during no-wind periods. When we optimize under these constraints, we obtain charging-discharging plans that greatly stabilize the output. We can show these figures, and they can improve the performance, especially on the unstable part of the region 2. Achieving stability in high fluctuating periods might even require increasing the battery capacity. And there is, however, important issue to consider. We cannot frequently cycle the battery because doing so would significantly reduce the lifespan. And to avoid this, we must maintain constant battery decisions over a set period. The consistent means we cannot wait to obtain actual wind speed data for the entire interval before deciding on battery operations. Instead, we must rely on historical wind speed estimates. To further enhance the flexible smoothing framework, integrating machine learning models to better predict the window speed may prove beneficial. And these predictive models can help refine battery charging and discharging decisions, leading to even more stable energy output while minimizing battery wear. And even with a stable power, we often face the problems of energy supply and demand mismatches. To improve the utilization of renewable power, we must address the issue through an effective workload um, scheduling strategy. And in this article, this challenge is tackled with a straightforward mechanism called active Active delays aims to optimize energy usages by intelligently scheduling tasks. For instance, consider scenario this one of in these figures. The blank space in the centers of the left-hand images illustrate a significant waste of wind energies. And by simply delaying the execution of job selected, we can capture the wasted energies and improve overall utilization. And let me explain the process with the procedural code. And for each incoming job, we can calculate its slack time, and which is defined as slack time equals to deadline minus runtime, and current time. And we can rank these jobs based on their slack time, identifying which jobs can be delayed. And for giving job in the scheduling queue, search for the optimal execution time within its available slack time. This optimal is defined as the moment that maximizes renewable energy usage. For example, assume this circle representation of demand, where the job slack time is 3, and there are 3 boxes. Each box is corresponding to different levels of wind energy supply. In these simple cases, the optimal execution time is at time 3, which yields the maximal utilization of wind energies. And for tasks with 0 or negative slack time, the system executes them immediately. While the adaptive delay algorithm is effective for deferrable workloads, it does come with challenges. And first, this approach is only applicable to tasks that can be deferred, does not address the real-time task requirements, and is relying on the greedy strategies, and we cannot guarantee a global optimal solution when we use the greedy strategy. And the approach requires a reliable forecasting of future energy resource. Without accurate prediction of future supply, scheduling remains fundamentally unfeasible.
Hi everyone, I'm Chunyi and I will introduce the following sections. To evaluate smoother, we configured a realistic test environment. Our setup included 11,000 servers, each with a peak power of 186 watts and an idle power of 62 watts. For workloads, we used 3 real-world traces: Google cluster data, web service logs from NASA and UC Berkeley, and batch job traces from HPC2N and other production systems. On the renewable energy side, we integrated window power data from the National Renewable Energy Laboratory, categorizing it into low and high volatility traces. Our key metrics were energy switching times, how often the system had to switch between grid and renewable power, and the renewable power utilization, which measures how efficiently green energy is used. Let's divide deeper into the data. The Google cluster trace, shown in Figure 8, provided a month-long snapshot of our power consumption patterns. For web workloads, we analyzed the logs from servers like Lassus, which averaged 29% CPU utilization. Batch workloads, such as those from HPC2N, allowed us to test deferrable job scheduling. On the renewable side, window power traces were split into regions based on volatility. This classification was critical for determining where flexible smoothing would be most effective. We focused on two main metrics. First, energy switching times, a measure of how often the system had to fall back on grid power due to renewable fluctuations. Fewer switches means greater stability. Second, renewable power utilization, which quantifies how much green energy was actually used versus wasted. For comparison, we used a baseline approach called COMP, which represents a standard battery storage solution without our optimizations. Flexible smoothing delivered significant improvements. By optimizing battery charge and discharge cycle, it reduced energy switching times by up to almost 30% in high volatility scenario, like the wind trace from May 18th. Even in stable conditions, such as May 2nd, we saw a small reduction. Figure 4 clearly shows the smoothing effect. Raw wind power with sharper spikes and dips becomes a steadier supply after processing. This stability is crucial for grid and system reliability. Scaling up wind capacity further validated our results, with 976 kilowatts of installed wind power. Flexible smoothing cut energy switching with a bigger reduction. At 1525 kilowatts, the reduction is less. However, there is a trade-off. More aggressive smoothing requires larger batteries, as shown in Figure 5. The takeaway: flexible smoothing is adaptable, but system designs must balance smoothing intensity with battery costs. Active delay tackled the second challenge: inefficient renewable power usage. By intelligently scheduling deferrable workloads, it increased renewable utilization by an average of 69%. For example, in the HPC2N trace, utilization jumped from just 19% to 21%. It's so big, right? The algorithm, detailed in Algorithm 1, prioritized the execution during periods of high renewable availability, as is illustrated in Figure 7. This ensures green energy isn't wasted when supply exceeds demand. Active delay adapts to varying power conditions. In Figure 14, with sufficient renewable energy. It shifts workloads to fully utilize excess supply. Conversely, Figure 15 shows it handles scarcity, differing non-critical jobs to minimize grid reliance. This flexibility makes active delay effectively regardless of renewable availability, a key advantage of real-world development. Together, flexible smoothing and active delay create a powerful synergy. Figure 17 shows that combining them reduces energy switching by over 25% compared to using active delay alone. This means greater grid stability alongside higher renewable utilization. The results were consistent across all workload types, Google, Web, and Batch, proving Smooth's versatility. In summary, Smoother addresses two critical challenges in renewable powered system. First, flexible smoothing cuts energy switching by at least 25%, stabilizing power supply. Second, active delay boosts renewable utilization by 169%, ensuring green energy isn't wasted. These improvements come without prohibitive battery costs, making Smoother a practical solution. Future work could extend these techniques to hybrid energy systems or solar power. For the first bonus question, while Smoothers show impressive results in simulation, its reliance on perfect renewable energy predictions is a key limitation. In the real world, sudden weather changes, like unexpected wind drops, could disrupt the smoothing process, leading to instability. To fix this, we could integrate machine learning for more adaptive forecasting. For example, a machine learning model could analyze historical weather patterns and real-time data to predict fluctuations more accurately. For the second question, we could combine the solar power into the original design. Thank you, everyone. Thank you.